In this first lecture, intended for a broad audience, I will summarize some steps that have led to the use of quantum mechanical systems, very simple quantum mechanical system, actually the simplest that can be thought of, that is quantum bits, two-level quantum mechanical systems. The use of these systems as computational tools. And during this lecture, the basic rules of quantum mechanics will be recalled in a kindergarten way, and they will be slightly investigated more deeply in the second and third lectures. I recall that quantum mechanics is now celebrating its 100th birthday this year, and actually this month. And I think a few days from now, Heisenberg was writing up his paper on the Helgoland Island that is considered more or less the official birth of quantum mechanics, together with the works of Schrödinger and Dirac and many other founding fathers of quantum mechanics. Okay, this is more or less the menu for the next lectures, where I will elaborate a little bit on quantum gates and circuits, not only on quantum bits, because one has to be able to manipulate, to control, and to operate on quantum bits, and this will be the topic of the second lecture, where we will speak about quantum circuits and give some examples given by teleportation and cryptography. And then we will discuss the more dramatically impressive algorithms of quantum computation, like Shor's algorithm for factorization and Grover's algorithm for research in a non-structured database. So this is the menu. Now, all of you know this experimental law, Moore's law, about dimensions and speed of computers, of processing units, of chips, which reduce roughly by half every 2 years. This has begun in the 50s from the thermoionic valves, and then it has, as you see, it's well approximated by a straight line, where you have the years in the x-axis and the number of components of chips in the y-axis. And if you extrapolate this trend, what you find is that around 2020, the dimensions, halving every 2 years, arrive at the scale of molecules and atoms, 10 to the 9, 10 to the 10 meters, which is the atomic scale or the molecular scale. And then one could think that this progression in miniaturization of computer components has to stop, because you arrive at the last bricks of nature. But progress doesn't stop, because at that scale you can use some new effects that enter the game, that are the quantum mechanical effects. And these are indeed can be exploited, and you can construct with atomic systems. You can implement algorithms that, as we will see in the course of this lecture and the next ones, which have the potentiality of being exponentially more efficient than those based on classical bits. Now, to run these algorithms, you need quantum computers. That is, you need computers based on microscopic systems where quantum mechanics is evolving the system and regulating the behavior of the system. And at present, we do not have commercial quantum computers. There are prototypes. These are some prototypes. They are based on various technologies according to what physical implementation of the bit, of the quantum bit you prefer, you choose for the construction and the manipulation of these quantum bits. And so you can have quantum bits that are carried by photons, carried by electrons, carried by microcurrents in superconducting rings, carried by ions trapped by electromagnetic fields. I mean, you have various technologies. And here there are some of these quantum computers illustrated. There are also educational online accounts that are thought to be used by students, which I encourage you to try. The IBM Quantum Experience have accounts that are free. One has a limited amount of machine time on these quantum computers. They can be programmed with a very easy graphical language, and one can really gain some experience in quantum computer programming. The number of qubits now is arriving around thousands of qubits. Most of them are not used for the logical computation that we will see in circuits, but are used for error correction. For error correction, you need a lot of redundancy. And error correction is important because, as you can understand, when one has to deal with microscopic systems, then one has to be able to manipulate the system, that is, to intervene on the microscopic structure, but at the same time, one has to isolate the structure from environment, because otherwise the interference of environment, the influence of environment on very tiny microscopic systems can destroy the information stored in the superposition of these quantum states. That is, provoke what is called decoherence. And so we have these two conflicting requirements in the construction of quantum computers that explain why it is a formidable engineering task to construct such machines. The idea of using quantum mechanical systems as computational tool goes back at least to 1981, when Feynman spoke at a conference that was titled Simulating Physics with a Computer, and where he was making the point that nature is not classical, and if you want to simulate it, you have better to use something quantum. And he was convinced that this would not be an easy task, and indeed it is not. This is the article that came out after the conference. It's slightly edited, but it's a beautiful paper. And the main observation was that if you use a classical computer to compute the evolution of a quantum system with n components, for example, a system of n atoms in a molecule, the number of steps that you need to compute this evolution using Schrödinger equation grows exponentially with n on a classical computer. But this could mean that you are not able to simulate quantum mechanical phenomena, with a classical computer. But then Feynman makes a leap and says, okay, but what if we use a computer that is made itself out of quantum mechanical components? And he makes a case where he proposes, indeed, to take this attitude. And taking this attitude means that, in theory, your quantum mechanical computer, since he manages to catch up with the exponential growing of computational quantum system, would solve also other problems in an exponentially more efficient way. And this was the hope that was manifested in this paper that has inspired then the evolution of this field of research. Now, I will just summarize the difference between a bit that is a classical system that can live only in two states, like a switch, state 0 and state 1. These are the symbols that I will use in this talk. In the next talk, I will use some more familiar symbols for physicists that are ket vectors in the notation of Dirac, but in this first lecture, I will call them state 0 and state 1. For classical systems, a switch can live only in these two states, but for a microscopic system, a two-state microscopic system, I will consider a simplified atom with only two states. If you want, with only two orbits for the electron, or better, only two possible energies for the electron bound by the electrostatic force to the nucleus. So I will call E0 and E1 the energies corresponding to the two energy levels, and I will call state 0 the one with lower energy, the smallest orbit. The fact now is that also the atom can be in two states, the state 0 and the state 1, but the new ingredient that we have in quantum theory is that it can live also in superposed states. And I call these superposed states state 0 plus state 1, okay? This is a superposed state, and you may ask what happens in this superposed state. What is the energy of this superposed state, for example? Now, the answer, now this is a pictorial way to see state 0, state 1, and the superposed state. The superposed state can be reached by sending a laser beam that has exactly the frequency that corresponds to the difference of energy between these two orbits. And if you insist with this beam for a prescribed time, you can create a superposed state. I mean, that's the way to create this superposition of states. But what characterizes the superposed state, and this is one of the first ingredients in the rules of quantum mechanics, is that if you measure the energy of the atom, the simplified atom in the superposed state, what you will find is not an energy intermediate between E0 and E1, like one could maybe think or surmise, but you will find either E0 or E1, always one of these two energies, but with a probability, okay? And the probability is given by this slight modification of what I wrote before for the superposition. Now you see I'm putting coefficients before state 1 and state 0, and these coefficients carry the information of what is the probability of obtaining the result E0 or the result E1. Okay, if you take the square of these coefficients, now don't worry what are exactly these numbers, but there is a way of extracting a square, something that is intrinsically positive, And this is the probability of observing E0 and E1. So in general, when you have a system that has two basis states, 0 and 1, a quantum system, what you can have is, and this is called the superposition principle, you can have a superposed state where what comes out is that it is a state where a measurement does not give any more a certain result with probability 1. It gives you a result with probability 1 only if A is equal to 1 and B is equal to 0. Then you will always find 0, E0. If B is equal to 1 and A is equal to 0, you will always find E0. But if it is in a superposed state, you find either E0 or E1 with a certain probability. And this probability is an intrinsic probability. It's not a probability due to our lack of knowledge. And this is why we say that quantum mechanics is intrinsically indeterministic. Oh, A and B must satisfy this rule because the sum of the probabilities has to be equal to 1. And you will notice that this qubit, now I call it quantum bit, that is qubit for short, has infinitely many states because these A and B can vary in a continuous way. They are usually complex numbers, but now just consider them as real numbers. And potentially this state can carry an infinite amount of information because you can vary in a continuous way these coefficients that are called amplitudes of the state. This is what more or less I was saying. This is an example of a superposed state where you see these coefficients are 1 over square root of 2. And if you take the square, it means that the probability of obtaining E0 is 1 over square root of 2 squared, that is 1/2, right? So the square of this plus the square of this makes 1. And this is the analog of a classical coin that you are throwing, except that it is not classical, except that after a single measurement of your quantum coin, you cannot tell what was the state before the result you have obtained. Okay? If you throw a classical coin and then you hide it, and then you look at it and you find that it is heads, it means that even before you uncovered it, it was heads. Now, this is not the situation anymore. The situation is that if you measure the energy, for example, of this simplified atom, what you will find is E0 or E1. But if you find E0, for example, well, it could have been in this state, because you can find E0 with probability 1/2, but it could also have been in the state 0. And then you would have found E0 with probability 1. But you don't have the information of what was the state before the measurement. You just know the result of the measurement. If you know the state, you can calculate the probability of the results in a measurement. But if you don't know the states and you obtain a certain result, you cannot deduce what was the state before. And this is a dramatic difference with the classical case. And we will see that it has some deep implications. One first application on the fact that you cannot distinguish from the state 0 and the superposed state can be exploited, in fact, to construct what is called quantum money, just by printing a string of qubits, never mind with what technology. Now, let's just suppose that we can, associated to a serial number, and that there is a very simple protocol that can be exploited to check whether the banknote is counterfeited or not. Because you see, a counterfeiter has to clone these qubits, but it is impossible to do so because he doesn't know what is the sequence of the qubits. The sequence of the qubits is known only by the bank that associates every sequence to a given serial number so that the shop owner that is selling goods to a client can check on a little machine communicated with the bank if the banknote is authentic or not. I will come back later in more detail on this possibility. Now, there is indeed another ingredient in these basic rules of quantum mechanics that we are using, and the basic ingredient is the effect of a measurement. The effect of a measurement on a superposed state is to make it collapse in either the state 0 or the state 1, right? And you understand why the banknote now is difficult to clone, because a counterfeiter should measure these qubits, but by measuring them, he will alter them, and by altering them, then he will not be able to reproduce exactly the same string of qubits on the banknote. Now, this is called the collapse of the state, or the collapse of the wave function. So the conclusion, which is far-reaching, is that measurements disturb the system, okay? And these are the two rules that I will use today and even tomorrow. I mean, these are the basic rules given in their most simplified way of quantum mechanics. Enter the probabilities, and you have unavoidable disturbation of the system when you measure it, okay? It is not so unexpected that the system is disturbed by measurement, because when you have a macroscopic object, of course, the photons that give me the information that this table is here are not displacing the table in any way, but you must imagine what happens if I try to localize an electron. To localize an electron, I have to take a photon and make it scatter against this electron. And since you have comparable energies, comparable momenta, then a disturbance is obviously unavoidable. So in the microscopic world, the fact that there is an intrinsic disturbance induced by the measurement is not something that is totally unexplainable, right? It's something that we could even expect. So observation is invasive, and in general, the state after the measurement is different from the state before, except when the state is state 0 or state 1. If it is state 0, you will find E0, and the state will collapse into itself, which is state 0. So this is the only case, these two extreme cases, A equals 0, B equals 1, or A equals 1, B equals 0, are the two extreme cases where you have no disturbance. But otherwise, in all other cases, you are modifying the system. Okay, so these are the rules of the game, and now we will try to apply it to see what consequences they lead to. Okay, thus we have understood that indeterminism due to probabilities is unavoidable, and it is one of the chief characteristics of quantum mechanics. Now, these rules can be applied also to a system of more than one qubit, more than one atom. If you have two atoms, for example, then you see that with state 0 and state 1, you can form 4 basic states, right? The first atom has energy E0, the second energy E0, or 0, 1, 1, 0, and 1, 1. You have 4 basic states, as they are called, where a measurement of energy on both atoms gives you a definite answer with probability 1, E0 is 0, E0 is 1, and so on. But what quantum mechanics tells us is that because of the superposition principle, is that you can have also states which are a superposition of these 4 states. And now the coefficients will be 4 of them, right? A, B, C, D, because you have 4 possibilities. And the squares of these A, B, C, D must sum to 1, because they are probabilities of obtaining E0 is 0 or E0 is 1, etc. The sum of the probabilities has to be 1. And again, after the observation, the state collapses into one of these 4 states according to the results that you have obtained. If you obtained E0, E1, then it will collapse into this state after the measurement where E0, E1 have been obtained. Okay, so now we have the rules of the game for multiple qubits, right? Because these were 2 qubits, but you can immediately extend this discussion to n qubits, right? Notice that for n qubits, here, before you had 2 terms in this superposition, now you have 4. For n qubits, it's easy to see that you have 2 to the n, right? Because these are the binary sequences of n bits. There are 2 to the n of them. And so the number of these amplitudes increases exponentially with the number of qubits of elementary quantum 2-level systems that you have. And you start to understand where resides the power or part of the power of quantum computing. That here you have an exponentially growing number of amplitudes that carry information. And when we will manipulate, we will operate on these states, we will operate with some operators that are called quantum gates. And these quantum gates are described mathematically, exactly like here. This is a mathematical description of a state, are described by what are called linear operators. And linear operators acting on such a state that will be considered a vector in an appropriate vector space operate simultaneously on all these superposed basic states. And there you can start to guess why quantum computing is potentially very powerful, because it has an intrinsic operation parallelism, because the operation on this state is really the operation on 2 to the n states simultaneously. And this will be exploited to enhance exponentially the computing capabilities of microscopic systems. What will be a delicate issue is to extract information from such superposed states, okay? But potentially they contain an enormous amount of information. Let's consider, for example, this state, and this is a particular superposed state where only 2 of these 4 basic states are considered for 2 atoms, 2 simplified atoms, or 2 qubits, and both with the same weight, this one. And this means that if you make an energy measurement, you will have 1/2 probability of finding E0 on the first and E0 on the second atom, and or E1 on the first and E1 on the second. But if you find E0 on the first, then it will be, the result on the second will be determined, because you cannot find something different from E0, E0 or E1, E1. So the result on the first atom somehow binds the results, conditions the result on the second atom. And this is what we mean by quantum correlation. The results of measurements are correlated, okay? And quantum correlation will be exploited quite heavily in quantum computing. Okay, we call these states where results are correlated, they have a name that you have heard certainly. They are called entangled states. So this state here is a typical example of an entangled state, and in fact it is named Bell state in honor of John Stuart Bell, that worked indeed on issues like the famous inequalities that are based on the existence of entangled states of composite systems. Now, notice an interesting thing, that these states are states of two atoms, and to create this kind of states, you need the two atoms to interact at some point, okay? So they have to be close together. But after having interacted and having created an entangled state between themselves, you can separate, in fact, them. And entanglement does not depend on distance. You can really imagine to separate them quite a long distance. You can put an atom on the Earth and the other one on a planet close to Alpha Centauri, and still they will be entangled. They will be in this global state, okay? You can give the first atom to Alice, the second atom to Bob, and Alice and Bob indeed can separate quite a lot. And if Alice measures the energy of her atom, well, Bob will obtain exactly the same measurement on his atom. 0 means 0 also for Bob, and 1 means 1 also for Bob, okay? Now, this happens if Alice and Bob measure. But the interesting thing is that you can imagine that only Alice measures her atom. If she measures her atom, she will find 0 with probably 1/2 and 1 with probability 1/2, because the state you start with is this state. And you see, this state has 1/2 probability of a measurement by Alice gives E0, and 1/2 probability that a measurement by Alice gives E1. So Alice will have a probability 1/2 of obtaining 0. But then we know that the system, since after a measurement the system collapses, the only way it can collapse is in the state 0, 0, because it's the only state that has a 0 in the first place. We had 0, 0 plus 1, 1. And if Alice finds 0, it means that the whole state has collapsed into 0, 0. And indeed, it collapses into 0, 0, whether Bob measures it or not. It is still an effect of the measurement of Alice. And here comes the non-intuitive thing. Something that Alice does on the Earth influences instantaneously the global system of the two atoms, which means also the global system that includes the atom of Bob that is 4 light years away. And this non-local effect can be tested, in fact, on the lab. Can be tested on the lab, and this non-local effect will be used for teleportation, but cannot be used for communication, because you could think, oh, okay, Alice is able to influence instantaneously the state of the system, even if part of the system is very far away from her. Maybe, for example, by deciding to measure or not to measure her atom, she can send a message to Bob, since measuring or not measuring has an effect on the global system. So you can ask yourself, but what happens if she tries to send a message to Bob? Is special relativity at risk because Alice manages to send instantaneously information 4 light years away from her? The answer is no, because she cannot do it. It's easy to see why. Because the statistics of Bob can only detect a measurement or an action on the state, on the global system, only if his statistics, his measurements on his atom vary in one occasion or in the second case where Alice doesn't measure, or in the case where Alice measures. But the statistics of Bob will never vary. Whether Alice measures or doesn't measure her atom, the statistics of Bob will remain the same. Bob will always have 1/2 probability of finding 0 and 1/2 probability of finding 1. And you can understand why. Because if Alice doesn't do anything, the state remains this superposed state, and Bob, like Alice, has 1/2 probabilities of finding 0 and 1/2 probability of finding 1. So his statistics is 50-50. What happens if Alice measures her state? Alice, if she measures her state, she has 1/2 probability of making it collapse to 0-0, 1/2 of making it collapse to 1-1. So Bob will still have 1/2 probability of finding 0 and 1/2 probability of finding 1. The statistics has a different origin, but the statistics is the same. So that Bob cannot decide whether Alice has measured or not. So you cannot use collapse of entangled systems to send superluminal information, okay? And so special relativity is safe. Now this is something not quite trivial, because you notice that we are discussing non-relativistic quantum mechanics. But somehow non-relativistic quantum mechanics, that is really first kindergarten quantum mechanics in this exposition, doesn't know anything about relativity. But somehow it is smart enough not to conflict with special relativity, which is kind of nice. This non-local action has been tested in the lab in the 80s by experiments in Paris by Alain Aspect, who won the Nobel Prize in 2022 together with Clauser and Austrian physicist. Please provide the name. Okay, they were three. Zeilinger, okay, the age. Using polarized photons as carriers of the quantum information, state 1, state 0 are associated to vertical and horizontal polarization of photons. So a generic state of a polarized photon, you can write it in this way, exactly like these simplified atoms. And you can make measurements not of energy in this case, but of polarization. Measurement of polarization are very easy to do. You can do it in a didactic lab, in the labs we have in first and second year physics, by polarizing filters and photon detectors that are slightly more expensive, but now they are quite available even in student lab. For example, you may have a state that describes a photon polarized with an angle of theta with respect to the vertical, and then this is the combination of the basic states. You will recognize that with this combination it will have the probability of passing a vertical filter, which is the square of this coefficient here, which is cosine square, and this reproduces the classical malus law for polarized light. So just remember that for a 45 polarized state, you have this state, here there is a 1 that has become a 0, but it's a misprint. You have this state that was the state that I was calling a quantum coin state, okay? This can be carried by a polarized photon at 45 degrees with respect to the vertical, and your measurement is with a filter that is vertical. So the photon has 1/2 probability of passing the filter, 1/2 probability of being absorbed by the filter. By sharing an entangled state, as we will see in the second lecture, we can, by entanglement, transmit in a 100% faithful way an even unknown state of a qubit from Alice to Bob. But this will require, as a quantum resource, this superposed state that is entangled, that is shared by Alice and Bob, like before between the Earth and Alpha Centauri. And Alice has additionally this qubit in a state that she wants to teleport to Bob, and this she can do by further entangling this state with her part of the entangled state, this Bell state, and then phoning to Bob the result of her measurements on this pair that she has. This will allow Bob, when Bob knows the result of these measurements by Alice, it will allow Bob to reconstruct exactly, by some operations on this state B that he has, to reconstruct exactly the state P. So this is the logical process of quantum teleportation that we will discuss in detail with the circuit in the next lecture. Now, this was the first proposal, the first theoretical proposal of quantum teleportation, and it is also the first example of the word teleportation in a scientific paper. In fact, Asher Perez was quite against using teleporting in the title of this paper, but the other authors convinced him that it could be okay. And then this is the first experimental verification of this protocol in just 3 years later. And while the first verification was 1 meter teleportation in the lab, now some years later, quantum teleportation was achieved over more than 100 kilometers between 2 Canary Islands, and now even with satellites, Chinese experiments. Okay, now since we will try to solve complex problems in an efficient way with quantum computers, I will now just recall a few things about complexity. As you know, there are easy problems and hard problems. Okay, but easy problems, now let's give a definition, are those whose solution can be found in a number of steps that grows at most as a power of the dimension of the input. The dimension of the input may be the number of digits, for example, of a big number that you want to factorize or you want to multiply by another one. For example, if the addition of 2 n-digit numbers, well, you have to do something like n operations, right? N elementary operations, so it scales like n. When you have to multiply 2 numbers n-digit long each, you have n-square operations and so forth. Okay, so these are all polynomial growing of number of operations required, and they are considered easy problems. They scale as powers. The hard problems scale in a super polynomial way, okay? So they scale in a way that asymptotically they win over any polynomial. They scale faster than any power of n. Factorization is an example. Factorization of an integer is an example where the number of steps scales exponentially with the number of digits of the number by the classical known algorithms. There is no known classical algorithm that scales less than exponentially, which doesn't mean that it doesn't exist. I mean, it is not known, okay? And accordingly, the complexity classes are divided into class P, which are problems that can be solved in polynomial time, class NP, which means problems whose solution you can verify in polynomial time, So factoring is one of them, because if I give you the factors, the prime factors of an integer number, you can verify quickly, because multiplication is easy, you can verify whether it is a solution of the problem. So factoring is an NP problem. And then you have an interesting subclass of NP problems, which are the NP complete problems, which are particular problems that are such that any other NP problem can be translated into them. There is a dictionary from any problem to an NP complete problem. So that NP, of course, includes P, because a problem that can be solved in polynomial time, you can obviously verify its solution in polynomial time. And the big question is whether NP perhaps coincides with P. There is no proof that it does not or that it does. So this is the graphical situation, if you want. You have NP that includes P, and inside NP you have the NP complete. And if ever an NP complete problem could be solved in polynomial time, then you understand that this would imply that P is equal to NP, because it means that every NP problem could be solved in polynomial time, which means every NP problem would become a P problem, okay? Now, this question is one of the 7 Millennium Prize problems. Now, you may think Millennium Prize means that if you solve it, you get $1 million, right? Now, you would think that NP-complete problems are exotic kind and very difficult problems, even to formulate, but it is not so, because some NP-complete problems are extremely easy to formulate. I will give two examples of NP-complete problems. The first one is a graph problem, where you ask yourself whether there is a Hamiltonian cycle in a graph. By Hamiltonian cycle, we understand a cycle, closed circuit, following the links of the graph, that touches all the vertices only once. All the vertices of the graph only once. This is a difficult problem classically. The number of steps you have to do to solve it is exponential in the number, for example, of vertices of the graph. Here, without the dashed line, there is no Hamiltonian graph, as you can verify immediately, because this is a very simple graph. And with the dashed line, of course, there is a closed circuit that visits all the vertices once, except the first one that is, well, you start from it and you return to it. So no polynomial algorithm is known. Now, if you could find a polynomial algorithm that solves this little problem, then you would conclude that P is equal to NP. And nobody has done it, of course. There is, and these are examples of Hamiltonian cycles. Surprisingly, and I would like to take out these things upstairs. Well, surprisingly, the same kind of problem involving links except of vertices is very easy to solve. And these are called Euler cycles, Eulerian cycles, closed paths that visit every link of a graph only once. It's called Eulerian cycles because it was a problem that Euler was asked to solve about the 7 bridges of Königsberg, today Kaliningrad. The inhabitants of Königsberg wanted to know if on Sunday they could make a trip passing through every bridge only once and returning to their home. And they could not find a solution, so they asked Leonardo Euler whether there was a solution, and he studied the problem. And the problem is completely solved. The graph has an Eulerian path, closed path, only if all the vertices of the graph have incidence number which is even. Incidence number means the number of links that are incident on the vertex. And since this was not the case for the Königsberg, this is the graph that reproduces the topology of the Königsberg bridges. And in this graph, you see that there are vertices that have 3 lines starting from them. So this cannot be an Eulerian graph. The second example I want to propose to you, and I propose it because it is simple and because it can be treated from a quantum computation point of view, and we will see how, is the partial sum problem. The partial sum is formulated like this. You have a string of numbers, n integers, and you are asked whether a subset of this set of numbers sums to a given number. I'm asking you, is there a subset that sums, for example, to 409? And this is a hard problem, classically, because classically what you have to do is to try every subset. And how many subsets are there of a set of n elements? There are 2 to the n subsets. And 2 to the n subsets means it grows exponentially with n, the number of these integers. So this is a hard problem classically, and no algorithm is known that is less than exponential. In this case, the answer is yes, because there is a subset that sums to 409, but in general, when you have millions of numbers, to find a subset is an extremely difficult problem. What will happen in quantum computation is that there will be an improvement. It will be an improvement, but notice also this is an NP-complete problem. So if the improvement in quantum computation would be making it polynomial, then within quantum computation we would have P equal NP. Unfortunately, this is not the case. The improvement will not be from exponential to polynomial. It will be from exponential to slightly less exponential, with an exponent that is half the exponent that it was before. So there is a quadratic improvement, but it is not, unfortunately, a polynomial algorithm. And it will be done with the Grover's protocol, as we will see. But what is dramatic and what really brought the quantum computation to the attention of not only the specialists is the dramatic improvement in factorizing integers. Shor's algorithm scales as n to the cube, where n is the number of digits, whereas classical factoring algorithms scale exponentially. So here there is really from exponential to polynomial time. And you understand that this integer factorization of class P in quantum computation has far-reaching implications for safety and for encryption. Because today the encryption protocols for credit cards, for example, are all based on the difficulty of factorizing integers, as we will see. Unfortunately, integer factorization is not NP-complete, because again, if it was NP-complete, then P would be equal to NP within quantum computation. I think that the Millennium Prize includes also quantum computation. So if you find a quantum algorithm that, for example, solves polynomially the partial sum problem, even in this case, you get $1 million. The current consensus is, however, that no polynomial time resolution for an NP-complete problem exists even within quantum computation, okay? So the general consensus is that P is different from NP, both in classical and in quantum computation. Okay. Since we were speaking about cryptography and the impact that factorization, quantum factorization, will have on cryptographic issues, I will just remind a few things about cryptography. There are essentially two ways of coding a message that you want to, whose secrecy you want to preserve. The one is essentially by alphabetic substitution, and then you sum modulo 26, I think, the letters of the alphabet with a key, and the result is some gobbledygook thing that is incomprehensible unless you know the key. If you know the key to decrypt this message, you just subtract modulo 26, the letters of the key. So the key is used both for coding and for decoding. But this is a risk, because if the key is using for coding and for decoding, this means that you cannot safely transmit it to all the parties that are interested in exchanging messages with you, because you have to send this key, and the channel in which you send the key can be a channel that is not safe. I mean, there can be intercepted. And if they intercept the key, since the key is the same for coding and for decoding, then they can decode the message. Malicious parties can decode the message. So symmetric coding has some vulnerabilities that are overcome by asymmetric coding. And this is the algorithm of Rivest, Shamir, and Adleman that even today banks are using for coding credit card numbers, for example. Here, the key for coding is public, but the key for decoding is private. So I can send in a public channel the key for coding the message without worrying about people reading it, because the key for decoding it is the secret key that, for example, only the bank possesses. And this uses some mathematical operations that are difficult to invert. I call them F here. A typical operation that is difficult to invert is indeed prime number multiplication, because if I give you the result of the multiplication of two prime numbers and I ask you what are the prime numbers, then this is difficult, whereas to multiply the prime numbers and obtain n, big N, is easy. So this is a typical one-way operation in the sense that it is difficult to invert. Now, the thing works more or less like this. You have a function that is based, that has as ingredient this n, which is the product of two big prime numbers, and then you have the message. And with this n, there is a protocol that encrypts this message, and you send to all the parties interested both the protocol and this n. You, of course, do not send P and Q, because P and Q are needed to invert this function and then to recover the message from n and the encrypted message. But this you can do only if you know P and Q. So in principle, you can always do it. If you are able to factorize n, then you can decrypt the message. But factorization of n is difficult. And so this is the reason why it is considered to be safe. To distribute the public key openly. Only the bank has the secret key, and when she received the coded message, your coded credit card number, then she can she can decode it. So this is the little cartoon. The public key is this open lock, and it is the public key, and Bob uses this open lock to close it on a box where he has his message, and he sends the box with the closed lock to the bank, and the bank has the key of this lock and can open it. Thus, quantum computers will allow, as we have seen, a fast decoding of this algorithm because of Shor's algorithm. Shor's algorithm will be able to factorize in polynomial time, which means that this whole protocol, RSA protocol, is at risk. But quantum mechanics, being a threat for these encoding algorithms, at the same time will offer a solution, and this solution is really quantum cryptography. Now, what time do I have? I'm finished. Okay, so this could be a good point to stop. Quantum cryptography, in fact, I was not going to discuss it in detail. It is based on the indistinguishability between superposed and basis states that I was mentioning before, but we will go through it in more detail tomorrow. Okay, thank you for your attention.